Good day, everyone. Our topic will be about angular momentum. This lesson consists of four main topics. These are rolling motion, angular momentum, conservation of angular momentum, and precision of gyroscope. But first, let us know what is angular momentum. Angular momentum is a rotational equivalent of linear momentum. It describes how object moves when they rotate around the axis. A simple way to think about it is that if an object is moving in a circle or spinning, it has angular momentum. It depends on how fast it rotates, how heavy it is, or how far its mass is from the center of the rotation. Meaning, angular momentum is how much spin an object has. Before we dig deeper, let us first know what is rolling motion. Rolling motion occurs when an object rotates while moving forward. It happens when an object both spins and moves at the same time. Think about it as a wheel or a ball rolling on the ground. It's not just sliding, it's also turning as it moves. It has linear motion because the object is moving forward, and rotational motion because the object spins around its centers. When rolling is smooth, it has no slipping. The faster it spins, the faster it moves forward. It has to meet the condition of tangential velocity is equal to radius times omega, or angular velocity. Rolling motion has two types: rolling motion without slipping and rolling motion with slipping. Rolling motion without slipping means an object rolls in such a way that it does not slide on a surface at all. It spins, moving forward, and the point of the wheel touching the ground is momentarily at risk, not sliding, but rolling. For example, a rolling ball. If it slides, it means it skids. Rolls without slipping, it moves smoothly like a bicycle wheel on a road. Rolling motion with slipping occurs when a friction is not enough. An object slides while rotating. It does not meet the condition of tangent velocity is equal to radius times omega.
So here's an example of rolling velocity. A ball that has a mass of 2 kilograms with a radius of 0.5 meters rolls on a flat road. Its center moves with a speed of 4 meters per second. Here is what we're going to find. Its angular velocity, which is our omega, and its total kinetic energy. So what is the formula of rolling without slipping? It is V is equal to omega times radius. Our V represents the tangent velocity. Our omega represents our angular velocity. And our R represents the radius. What we are going to find is our angular velocity. So we are going to transpose. What will happen? The omega will be transposed here, and our tangent velocity will be transposed here. So our formula would be omega is equal to velocity over r. Why over? Because multiplication would be division if we transpose. So we substitute. Our tangent velocity is given already. This will be our tangent velocity. Why? Because it is the center of our object. Our radius is already given. It is 0.5 meters. Then we divide, it will be A radius per second. And that would be our angular velocity. Next, we will have to find the total kinetic energy.
What is total kinetic energy? Total kinetic energy is seen or present an object rolls forward or moves forward. Total kinetic energy is the result of adding translational kinetic energy or rolling energy.
Total kinetic energy has two parts. It is the translational kinetic energy and the rotational kinetic energy. The translational kinetic energy is the motion of moving forward. Its formula would be is equal to 1/2 mv squared. The rotational kinetic energy is the spinning. Its formula would be KE is equal to 1/2 I omega squared. That would be our two parts. Combining the two, we will have the total kinetic energy. Its formula would be total is equal to 1/2 mv squared plus 1/2 I omega squared. And this would be our total kinetic energy formula.
In solving total kinetic energy, let us first solve for our translation kinetic energy. So our formula is 1/2 over mv squared. This is our given. So let us just substitute 1/2. Our mass is 2 kg. Our velocity is 4 meter per second square. So the result would be 16 joules. Next, we'll be solving our rotational kinetic energy. However, we have to find our inertia first because it was not on the given. Our formula for inertia would be based on the object that is used. Our object is Our object is a solid sphere. So our formula is inertia is equal to 2/5 2/5 mass radius squared. Let us just substitute 2/5. Our mass is 2 kg. Radius is 0.5 square. This would be 4/5, 0.25, and it would result to 0.2. So now we have found our inertia. We can now solve for our rotational kinetic energy. Rotational kinetic energy has the formula of 1/2 inertia omega squared. Let us substitute. We have our inertia here and our radius. This would be 6.4 joules. And now we have our rotational kinetic energy and translational kinetic energy. We just have to add the two to get our total kinetic energy. And that is how we get our total kinetic energy. Our next topic would be angular momentum, which will be discussed by Vince DiMario.
Angular momentum. Angular momentum is a vector quantity that measures an object's rotational motion just like linear momentum describes how hard it is to stop something moving in a straight line. Angular momentum tells us how hard it is to stop something from rotating. The key point is angular momentum is conserved when no net external torque acts on the system. This is similar to how linear momentum is conserved when there's no net external force. Let's start with a single particle. For a single particle, angular momentum L is defined as the cross product of its position vector r from the origin and its linear momentum P equals mv, where L is equal to r times P. The direction of angular momentum is perpendicular to the plane formed by r and P, and we determine it using the right-hand rule. Its magnitude is L is equal to r times P sine theta, which can also be written as L equals r perpendicular mv, where r perpendicular is the distance lever arm from the origin to the line of motion. Finally, the time derivative of angular momentum gives us torque, where dl over dt is equal to t. So if angular momentum is constant, the net torque about the origin is 0. Here's an example. A meteor is at position r equals 25.0 km plus 25.0 km at a certain instant. Its momentum is changing with time. We calculate its angular momentum at t equals 0 and find its 7.50 times 10 to the power of 8 kilogram times m squared s is the negative z direction. Interestingly, even though both r and v are changing, the torque remains constant because the lever arm and the force stays perpendicular. This shows how powerful the concept is in a real-life scenario. Now for a system particles in a collection of point masses, the total angular momentum of the system is simply the vector sum of the individual angular momentum. L is equal to L sub 1 plus L sub 2 plus so on plus Ln is equal to summation of L sub I, and the next external torque equals the rate of change of the total angular momentum dl over dt is equal to summation of torque I ext. This is the rotational version of Newton's second law for system. Here's an example with three particles. We're given their masses, position, and velocities by calculating L is equal to R times P for each particle and adding them up. Vectorially, we get the total angular momentum of the system as negative 30 kg squared per second in the k-hat direction. This kind of problem helps us practice the vector nature of angular momentum. For rigid bodies rotating with angular velocity omega about a fixed axis, the angular momentum simplifies to angular momentum equals I for inertia omega, where I is the momentum of inertia about the axis. The direction of L follows the right-hand rule along the axis of the rotation. Key insight: angular momentum is conserved. L is equal to constant whenever the net external torque about the chosen origin is zero. The single principle explains the ice skater effect, spinning faster by pulling arms in, planetary spin stability of rotating machinery, and gyroscopes. So here's an example. A robot arm on Mars. Model the arm as a rod and calculate the moment of inertia with and without the rock it's holding. Without the rock, L is equal to 0.17 kg squared. Second, with the 1.5 kg rock, L increases to 0.32 kg squared second. We can also calculate the torque needed to accelerate the arm at a given angular acceleration using the torque equals the moment of inertia multiplied by the angular acceleration. In conclusion, angular momentum is a fundamental concept in physics that governs rotational motion. It is conserved when the net external torque is zero. This is beautiful conservation law explains many everyday and cosmic phenomena, from ice skaters spinning faster by pulling in their arms to the stable rotation of planets and the behavior of rigid bodies like robot arms and flywheels.
So the next topic is the conservation of angular momentum. The conservation of angular momentum states that if the net external torque acting on a system is zero, the total angular momentum of the system remains constant over time. So if kung wala daw external torque nag-act sa system, iyang total angular momentum is remain constant lang. Iyang formula is angular momentum equals moment of inertia times angular velocity, where L is the angular momentum and I is the moment of inertia, and for the omega is the angular velocity. The conservation principle written as L sub 1 equals L sub 2, or I sub 1 times omega sub 1 equals I sub 2 times omega sub 2. So for example, a figure skater is spinning with an initial angular velocity of 2.0 radians per second with her arms extended. In this position, her moment of inertia is 6.0 kg/m². She then pulls her arms close to her body, reducing her moment of inertia to 2.0 kg/m². Assuming there is no friction or other external torques, find her new angular velocity. So, yung first nga angular velocity is 2.0 radians per second. Then, ang iyang first nga moment of inertia is 6.0 kg/m². And the second moment of inertia is 2.0 kg/m². So, this time, atong i-find ang iyang second nga angular velocity. Since there is no net external torque, angular momentum is conserved. So, ato siyang i-write sa equation nga katong I sub 1 times omega sub 1 equals I sub 2
times omega sub 2. So we need to substitute na dayon. Ang katong I sub 1 is, which is katong 6.0 kilogram meter squared times ang ihang angular velocity nga 2.0 radians per seconds equals sa iyang ikaduha nga moment of inertia nga 2.0 kilogram meter squared times sa katong second angular velocity nga need pa nato kuhaon. So ato nang isolve ang iyang second nga angular velocity. So 6.0 times 2.0 divided by 2.0. So 6.0 times 2.0 is mo equal siya og 12. So atong i-divide sa 2.0, so mo equal siya og 6.0 radians per seconds. So the skater's new angular velocity is 6.0 radians per seconds. To conclude, the conservation of angular momentum explains how rotational speed changes when the distribution of mass changes. It is widely observed in sports, space motion, and mechanical system. So, another explanation para mas masabtan kung unsay meaning sa conservation of angular momentum is that the total initial angular momentum is mo equal siya sa iyang total final angular momentum for a system with no net external torque. So, for quick pattern to remember, if the moment of inertia decrease, ang iyang angular velocity is mo increase. And if the moment of inertia is mo increase, the angular velocity is decrease. So that's all. Thank you.
Good day everyone. Today I will discuss about gyroscope and precision. First, let's define what is gyroscope. So what is gyroscope? A gyroscope is a device used to measure or maintain orientation and angular motion. It works based on the principle of angular momentum. When an object like a wheel or desk spin rapidly, it tends to stay in current position and resist change in direction. In simple term, if we spin, lisod siya, ilihok, or iliko. Let's go to the concept of angular momentum. One important concept here is angular momentum. Angular momentum is a tendency of rotating object to keep spinning unless an external force act of it. So kung walay disturbance, padayon ra gyud siya og tuyok. Stability. A gyroscope is defined as spinning disc where the axis of rotation can move freely in any direction. When it's spinning, its orientation remains stable even if the base is moving. So mao nang kuan, stable kay siya. So application of gyroscope. Gyroscope are used in many real-life applications such as airplane for navigation and stability. So next is ship to maintain direction. Next is smartphone for screen rotation. So kabantay mo ng mga smartphone nga kung ato i-rotate mo, rotate pod ang iyang screen. And sa motorcycle pod na pod siya for balance. So makita nato ang importante jud siya na technology. So concept of precision. Now let's move on to precision. Precision is the slow change in direction of axis of rotating object. Instead of falling over when pushed, spinning object moves sideways. So dili siya diretso matumba, mulihok siya pa sideways. So torque and angular momentum. This happen of torque. Torque is a force that causes rotation. When torque is applied to a spinning object, it changes the direction of angular momentum, not its magnitude. Mao nang instead nga matumba mo process siya. So example, spinning bike wheel. So let's consider an example. Imagine a person holding a spinning bike wheel. When the person tries to tilt the axle, the wheel does not simply fall. Instead, it rotates towards the person. This happens because the applied force creates torque, which shifts the angular momentum sideways. This motion is what we call precision. To summarize, a gyroscope maintains orientation due to angular momentum. Torque changes the direction of motion. This change result is precision. So for solving, so given is mass. So 0.3 kilogram, radius is 5.5 cm. Spin is 20 revolution. Ang distance to cm is 5.0. So calculate. So step 1 is find the inertia. So ang inertia na to is 3.75 times 10 to the power of negative 4. So ato na siya i-substitute diri. So 3.12. Step 3 is kanina na ato makuha na answer. So 2.0 seconds.